Problem F13-13. Determine the constant angular velocity theta dot of the vertical shaft of the amusement park ride if phi right there equals 45 degrees. Neglect the mass of the cables and the size of the passengers. So it's a constant angular velocity, so we have no acceleration in the tangential direction. So we have just the R and the Z direction to worry about. So if we sum the forces, well, first if we draw a free body diagram, we have tension coming that direction, and we have mg down. And if we sum the forces in the radial direction, the net acceleration is going to be inward at mv squared over r. And the only force that is in the radial direction is F. So if we call that F, the force in that direction is going to be F, there's theta, or phi, there's phi, F sine, or cosine phi. It's 45 degrees, so sine of phi, cosine of phi are both 0.707. So 0.707 F inward, and that will equal mv squared over r. Now if we sum the forces in the z direction, okay, we know that that's going to be equal 0 because there is no acceleration in the z direction. So we have 0.707 F, that is the vertical component, upward minus mg down. Those equal 0, so we could solve for F. F then is equal to mg over 0.707. Substituting this into the original equation, we have mv squared over r equals 0.707 times F mg over 0.707. Those cancel. M's cancel. And v is equal to g times r square root. Now the velocity at which it's swinging is going around, so we can use the equation v equals omega r, because we want to find omega, which is the same thing as theta dot. So omega r equals the square root of gr. Omega equals the square root of gr over r. Substituting in, g is 9.81. R is this distance here, which is going to be 1.5 plus 8 times 0.707, which equals 7.156. Divided by 7.156, and omega is equal to 1.17 radians per second.